The Butterworth filters are named after their inventor, the British physicist Stephen Butterworth. Their frequency characteristic is given by the magnitude of h of omega of a Butterworth filter squared is equal to 1 divided by 1 plus omega over omega c to the power of 2n, where n is the order of the filter, where omega c is the cutoff frequency. You will also often find the formulation that this is equal to 1 over 1 plus omega to the power of 2n, where the frequency is normalized. The normalized frequency omega is defined to be omega divided by omega c, where this omega here is again the real frequency. Unfortunately, the same symbol omega is used for the real frequency and the normalized frequency. And we will also use the normalized s, which is defined equivalently as s equal to the real s divided by omega c. Again, we use s for the real s and the normalized s. The standard Butterworth filter is a low-pass filter, but at a later stage we will see how a low-pass filter can be transformed into a high-pass, bandpass, or band-stop filter. The transfer function of the Butterworth filter of order 1 is given by 1 divided by s plus 1, where s here is normalized, so that we can write that this is h of omega c times s to symbolize that s here is the normalized s. Then, by replacing the normalized s by the real s divided by omega c, we'll give that h of omega c of s divided by omega c, so that omega c cancels out, which is equal to h of s is equal to 1 divided by s divided by omega c plus 1, where now the expression is given in real s. The transfer function of the second order Butterworth filter is given by h of omega cs equal to 1 divided by s squared plus the square root of 2s plus 1. The transfer function of the third order Butterworth filter is given by 1 divided by s plus 1 times s squared plus s plus 1. In the script and in many textbooks you will find forms for higher order Butterworth filters. The general transfer function of the Butterworth filter in normalized s is given by h of omega cs is equal to 1 over the product for k equals 1 to capital N, where n is again the order of the filter, of s minus pk, where pk is the kth pole of the system. The poles of the Butterworth filter are located on a unit circle in the S-plane. To find their location, place 2 n poles on the circle. This means that we need to start with twice as many poles as we will need for the filter in the end. The poles have to be evenly distributed around the circle, symmetric with respect to the imaginary axis, and as far away from the axis as possible. For example, for a first-order filter, we need to place 2 poles that are symmetric around the axis and as far away from the imaginary axis as possible, so that we will place them at -1 and at +1. Then only the stable poles are chosen to form the filter, so that the first-order Butterworth filter has a pole at -1. For the second-order Butterworth filter, we will now place 4 poles on the unit circle. Again, they have to be evenly distributed and as far away from the axis as possible, so we will place 4 poles at the angle of 45 degrees. Again, we only choose the 2 stable poles to form the second-order Butterworth filter, so that the poles are complex conjugates, with the real part being minus the square root of 2 and the imaginary part being equal to plus or minus the square root of 2. Following the same rule, we find that the poles of the third-order filter are 60 degrees apart, and again we choose the 3 stable poles to form the filter. The cutoff frequency is defined to be the frequency for which the magnitude of h of omega at this frequency is equal to 1 divided by the square root of 2. Going back to the frequency response of the Butterworth filter in real frequency, this is equal to 1 divided by 1 plus frequency, which is now omega c, divided by omega c to the power of 2n. And because we take the magnitude and not the magnitude squared, we also have to take the square root. However, this is always equal to 1 divided by 1 plus 1, and taking the square root out of this, which is 1 divided by the square root of 2. Hence, the normalization or denormalization using the cutoff frequency omega c makes sense. This way we ensure that the cutoff frequency of a Butterworth filter always lies at omega c. The DC behavior of the filter, or the zero frequency behavior, is given by the magnitude of h at 0, which for the Butterworth filter is always equal to 1 for all orders capital N, which means that DC input signals are always scaled with 1. Another property that all Butterworth filters have in common is that they are maximally flat, which means that the first derivative with respect to the frequency omega of the magnitude of the frequency response squared at the frequency equal to 0 is equal to 0 for all n. Another important property of a filter is its roll-off rate. In order to get a transition band that is as narrow as possible and hence to get as close as possible to the ideal filter, the roll-off rate has to be as big as possible, because it is given as the first derivative with respect to omega of the logarithm of base 10 of the magnitude of the frequency response squared at the cutoff frequency. For the Butterworth filter, this is equal to minus n, which means in order to increase the roll-off rate and to get closer to the ideal filter, we have to increase the order n. And with this, we mean the magnitude of the roll-off rate, because for a low-pass filter, the roll-off rate will always be negative. When we plot the magnitude of the frequency response of the first 4 Butterworth filters, we can see the influence of the order n. For the first order filter, here given in blue, the roll-off rate is relatively slow. But when increasing the order to 2, which is here illustrated as the green curve, or 3, which is the red curve, or even to a 4th order filter, the roll-off rate increases. If we want to have a filter with a sharper transition, we need to increase the order n. The Butterworth filter has only one decision variable, which is the order n, so the design process is relatively simple. All we have to do is to choose a suitable order n. For this, we need to calculate Gp, the gain of the passband, which is given by 1 divided by 1 minus delta p squared minus 1, and Gs, which is the gain of the stopband. It's given by 1 divided by delta s squared minus 1. Then the approximate formula for n is given by 1/2 of the logarithm of Gp divided by Gs divided by the logarithm of omega p divided by omega s. Keep in mind that omega p is the passband frequency and omega s is the stopband frequency. In general, the cutoff frequency is given by omega p divided by Gp to the power of 1 divided by 2n. If we know that the frequency response in the passband is allowed to be as low as 1 divided by the square root of 2, which is equivalent to minus 3 dB, the formula for n can be simplified. Then it is approximated by the logarithm of Gs divided by the logarithm of omega c divided by omega s, where in this case omega c is equivalent to omega p. Of course, the order of the Butterworth filter can only be an integer value, so in the end the order n has to be the lowest integer value which is greater or equal than the result of the approximation formula. For instance, if the approximation formula gives us a value such as 2.8, the order has to be chosen equal to 3. Let's consider a simple example. Assume that we want to design a low-pass filter where the passband ripples are allowed to be up to plus minus 3 dB, which means that 1 minus delta p is equal to 3 dB, which in real numbers is equal to 10 to the power of minus 3 divided by 20. This is approximately 1 divided by the square root of 2. The passband frequency is to be fp equals 1 kHz. We can also express this as omega p, which is equal to 2 pi times fp, which is 2000 times pi radians per second. The stop band attenuation has to be at least minus 30 dB, which implies that delta S is equal to 10 to the power of minus 30 divided by 20, which is minus 30 dB in real numbers. And the stop-band frequency is to be Fs equals 2 kHz, so that omega S is equal to 4000 pi radians per second. To find the order n of the system, we first have to calculate Gp equal to 1 divided by 1 minus delta p squared minus 1. Keep in mind here that 1 minus delta p is already 10 to the power of minus 3 divided by 20. So this is equal to 1 divided by 10 to the power of minus 3 divided by 20 squared minus 1, which is equal to 1. Gs is equal to 1 divided by delta s squared minus 1, equal to 1 divided by 10 to the power of minus 30 divided by 20 squared minus 1. This is equal to 999. Inserting those values of Gp and Gs together with omega p and omega s into our formula for n gives that this is equivalent to a half of minus 3.0013 divided by minus 0.3013, which is equal to 4.9856. Hence, we have to choose the order n equal to 5. The transfer function of the Butterworth filter of order 5 in normalized S is given by h of omega cs is equal to 1 divided by s plus 1 times s squared plus 0.618s plus 1 times s squared plus 1.618s plus 1. Because the passband ripples are allowed to be up to minus 3 dB, omega p is equivalent to omega c here, equal to 2000 pi radians per second. So that the transfer function of the filter in real S is given by h of s equal to 1 over s divided by 2000 pi plus 1 times s divided by 2000 pi squared plus 0.618 s divided by 2000 pi plus 1 times s divided by 2000 pi squared plus 1.618 s divided by 2000 pi plus 1.